Hello everyone and good morning. Welcome to the lecture series of VLSI technology with the subject code KEC 053 as per the AKTU syllabus scheme. We were discussing this is the lecture 6 and we were discussing the vapor phase epitaxy. So let us see the glimpse of the last lecture quickly, that what we have already discussed is what is epitaxial process and what is the need of epitaxial layer. What is the need of epitaxial layer? How many types of epitaxy are there? That is homo epitaxy and heteroepitaxy, right? What are the method used to grow the epitaxial layer? That we can classify it as liquid phase epitaxy, vapor phase epitaxy and molecular beam epitaxy. We have discussed about vapor phase epitaxy, that how we and we get to know about the starting material, that what could be the starting material in case of vapor phase epitaxy, and we will get to know about the process parameters that are required for the VPE, that is vapor phase epitaxy. Now, because in VLSI technology the major thing is the optimization. We have to optimize the things, that how we can reduce the temperature, how we can reduce the pressure, and how we can optimize all those things in the VLSI technology while manufacturing our IC. So, what should be the pressure and what should be the temperature for any process, and what are the other requirements that are required for the vapor phase epitaxy, that we are going to discuss in this lecture. So, if we talk about temperature, we know that this VPE, first thing is VPE is a high temperature process. Right? This VPE is a high temperature process. Now, higher the temperature, higher will be the surface mobility. Atoms will have more time so that they can get oriented to the particular direction. They can have sufficient time so that they can orient themselves to the as per the wafer orientation, and finally they will maintain the crystal orientation of the substrate, right? So, this is the advantage of the higher temperature, that when we work at the higher temperature, they will have more surface mobility and they will have more time so that they can get oriented to the crystal orientation of the substrate. But the major drawback of this high temperature is there will be more thermal stress on the wafer. If there is more thermal stress on the wafer, the chances are the dopants will be mixed to the epitaxial layer. Suppose we have this N type or P type substrate, this we have this P type substrate. Okay. Now, because of this high temperature, the chances may occur that the atoms present in this P type substrate, they get out diffuse. They may get out diffuse, and during the growth of the epitaxial layer, they get mixed with the compounds and finally resettle themselves as a epitaxial layer. Next is pressure. What could be the boundary? What could be the pressure required to have a boundary layer? The boundary layer states that Y is equal to dx by Nr, where Nr is the Reynolds number, right? X is the distance along the chamber, mu is the mobility, V is the velocity, this is the density of the gas, right? So, if your velocity is increased, the boundary layer will be decreased, right? We can see from the equation, if the velocity is increased, this boundary layer will be decreased and we have the less boundary layer problem. But if you increase the velocity, the gas flow will be increased, higher will be the gas consumption and more consumption of reactants will be there, and this will lead to the increase in cost of the overall system, because if you increase the velocity of the gas, your gas consumption will be increased, requirement of gases will be increased. So if we operate at the lower pressure, we can afford the, if you operate at lower pressure, we can afford the high velocity at the same consumption of reactant materials, and the boundary layer problem can also be reduced simultaneously, right? So the boundary layer problem can also be reduced simultaneously. So there are some additional benefits, like if you reduce the pressure, then the convection effects can also be minimized, and you can have a better temperature stability, right? And the variation of epitaxy is also called low pressure chemical vapor deposition. This variation of epitaxy is also called, when your epitaxial process is carried out at lower pressure, it is also called low LPCVD, and the pressure for this event is 20 to 200 torr. And we are using these two terms, one is epitaxy and the another one is low pressure chemical vapor deposition. There is not much difference between these two processes. In case of vapor phase epitaxy, it is nothing but a chemical vapor deposition process. We are depositing the layer of chemicals which are in the form of vapors, right? So it is the part of chemical vapor deposition process, but when we talk about this only chemical vapor deposition process, we generally do not specify whether the layer which is going to be deposited is crystalline or not. The chances are some polycrystalline layer may be deposited during the process of this CVD, chemical vapor deposition process. So we say that vapor phase epitaxy, it always means that it will give you a crystalline structure. The layer which is deposited above the surface of the wafer, it will be crystalline throughout the distance. Okay, so VPE is the subset of CVD. We can say that all VPEs, all vapor phase epitaxies are chemical vapor deposition process, but all chemical CVDs may not be your VPE. So next is that how we can select the compound, what compounds we can use, what are the compounds we can use to deposit the epitaxial layer. In the last few lectures we have studied that we have silicon tetrachloride, silicon trichlorosilane, then silicon dichlorosilane and Celine. We have the 4 compounds that can be used as a material to deposit the epitaxial layer. In the first part of the reaction, your the silicon tetrachloride, for example, your silicon tetrachloride, it reacts with the hydrogen and it will form SiCl2 and HCl. And in the second reaction, it is reacted with the silicon wafer and it will give you silicon and SiCl4 as a compound. So this reaction, so this is the important point, that this SiCl2 then get absorbed on the sample surface and it will form the silicon and SiCl4. So this important point is here that the presence of sample surface should be there, and it forms so that it can form silicon and silicon tetrachloride. And there are some more subreactions which will be carried out. So like we said, there are subreactions. It could be when your silicon tetrachloride, it is reacted with hydrogen, it will give you SiHCl3, that is silicon trichlorosilane plus hydrochloric gas as a byproduct. When this silicon SiHCl3, it is reacted with again hydrogen gas, it will give you SiH2, Cl2 and HCl gas. When it is further reacted with hydrogen, it will form this SiH SiH3Cl and HCl gas as a byproduct. So these reactions are chain reactions. When we start from SiCl4, the concentration of this chloride will be varied. So only when your SiCl2 is absorbed on the sample surface, your reaction is going to take place. Your reaction will be taken place, and this is called the surface catalyzed reaction. This is one important step. This is one important parameter, that the presence of wafer should be there. Secondly, as the concentration of SiCl4 silicon tetrachloride increases, as you see in the previous reactions, the overall reaction can also be written as this. Silicon tetrachloride, when it is reacted with hydrogen, it will give you silicon and HCl. This reaction will be carried out in forward direction. If your silicon tetrachloride, if the value of this silicon tetrachloride is increased, the reaction will be in forward direction and your growth rate will be increased. But a point may come that up to how much level we can increase the concentration of SiCl4, silicon tetrachloride. A point will come after that point. Instead of growth, your etching will start occur. So we will have a graph like this. Here we have the growth rate, and here we have the concentration of SiCl4. So up to certain level we will have the growth, and after that point your growth rate will start decreasing and your reverse reaction will take place and etching will start, etching process will be started. So what compound we can use as a starting material, whether we can start the reaction from this SiCl4, SiHCl2 or SiH2Cl2, this, okay. So from where we can start the reaction? Out of these or four, SiCl4, this is the most popular for industries. The silicon tetrachloride is most popular for the industries, because this silicon tetrachloride is insensitive to the oxygen traces which are present in the reaction chamber, okay. And if you compare all three, this SiHCl2 is sensitive to the oxygen traces. We may get the oxide of this compound, and this compound is also sensitive to the oxygen traces which are present in the reaction chamber. This another difference between these compounds is the formulation of this SiCl2 is done at 1000 degree C, whereas the formulation of SiCl2 can be done at lower temperature, and same for this case, this can also be done at lower temperature. If you talk about efficiency, the efficiency which is defined as the amount of silicon deposited, how much silicon we are going to deposit on the silicon wafer, divided by the amount of silicon present in gas. This is the formula for efficiency. If you talk about efficiency, this compound has the highest efficiency, and this silicon tetrachloride has the moderate efficiency. So we can manage these two drawbacks, because the oxygen is the most dangerous part in the reaction chamber. There should be no traces of oxygen in the reaction chamber. So that is why this silicon tetrachloride is preferred, because it is very much insensitive to the reaction chamber. If some oxygen is present in the reaction chamber because of the chamber materials, the oxygen will not precipitate in the end result, that is your epitaxial layer, and all these reactions will have HCl as a byproduct. So, and that is a very dangerous gas. So, all the reactors should have a very excellent venting out system. One another route is there, that is known as pyrolytic decomposition of Celine. So, this Celine, that is SiH4, is pyrolytically decomposed into silicon and hydrogen, and the reaction is SiH4, it will give you silicon and hydrogen gas. The advantages of using this process over the chlorosilane process is no HCl gas will be there as a byproduct. The reaction will be taken place at lower temperature, that is 500 degrees C. Silane, but silane will start decomposing, and finally this reaction is a non-reversible. Okay. So, after growth the etching process will not be there in this case, but the major drawback in this case is it will give you a very abrupt layer. It is not possible to have a very good epitaxial layer. Next is cleaning, that how the cleaning should be done inside the chamber. It is not possible that we take out the sample wafer outside the chamber and clean it and again put it back to the chamber. So, all the samples which have been loaded into the reactor chamber without taking it out, the cleaning inside the chamber, there must be provision for the cleaning and etching the sample. This cleaning and etching is normally done in two ways. The first one is the wafers are introduced in the reactors and they are flushed in dry hydrogen at about 1200 degree C, which is a very quite high temperature, and this 1200 degree C, this hydrogen, this dry hydrogen is passed through the reaction chamber and it will clean the surface. Next is we can pass the anhydrous hydrogen chloride, which is diluted with the hydrogen, and the etching process can be started. So, this is as a resultant, this reversible reaction can be achieved. Next is doping and auto-doping. In case of epitaxial process, some of the dopants, that is boron, arsenic, and phosphorus can be added to the epitaxial layer, and the limitation of this epitaxial growth is the unintentional doping. In addition to the deliberate doping that you want to introduce in the epitaxial layer, there is a possibility that the epitaxial layer can be unintentionally doped, and that is known as auto doping or automatic doping. The reason for this auto doping is due to the solid state diffusion and due to the gas phase auto doping. Before the epitaxial growth take place, the sample is being treated at very high temperature, right? We know that your sample will be is at very high temperature. So, it is possible that the dopants which are already present in the substrate, they may out diffuse and will change the composition of the gas stream, right? As I have already discussed, the dopants which are present in the substrate, they will out diffuse, they will get mixed with the compound gases, and then again they will be reintroduced in the epitaxial layer. So, the gas stream composition is controlled and depending upon the level of the doping in the epitaxial layer that you want to grow. Now, suppose we want to add some impurities and along with the silicon, but already present dopants in the substrate layer will be out diffused and modulate the composition of the gas stream, so that when the epitaxial layer is being grown, these dopants which are originally present in the substrate can now get back and reintroduced in the epitaxial layer. So thereby doping concentration of the epitaxial layer will be changed, right? So this will not follow the exact requirement of your epitaxial layer. This is done because of the solid state diffusion. Your dopants will be out diffused, and the another out diffusion. This is as the epitaxial layer is being grown. If the doping concentration of the substrate and the epitaxial layer is different, that is most of the cases we have the doping concentration more in case of substrate, and in compound in the gaseous form we have the less doping concentration. So they will also modulate the doping concentration, and deliberate doping concentration of your epitaxial layer will be there. And between bulk and the epitaxial layer there is going to be a transition layer which is determined by this by this effect of auto doping. So this is the graph for the doping and auto doping. Here we have your low concentration, that is your in case of gas phase, where your dopants are present in the gaseous form, and this is the solid state out diffusion, which is they are out diffused. They are out diffused from the surface of wafer, and we know that your wafer contains more doping concentration as compared to your gases. So this is one important graph which shows the doping concentration as a vertical width. It has, the graph is shown as in this direction when we go down in the direction. Okay, so here we have the gases and here we have the solid wafer. Okay, so this is the vertical depth, we have the epitaxy, and then we have the substrate. So at substrate end your maximum auto doping will be the maximum dopants will be there, dopant concentration will be maximum, and at gas phase your dopant concentration will be less. So this is how your impurities of hydrides will be placed in the epitaxial growth. For example, we have the arsenic impurity that we are diffusing in the silicon. They will react with the silicon material and will be distributed in this manner. This is the dopant incorporation process. Next is what are the defects present in the epitaxial layer. That there will be some defects which will be present in the last product, at the end product. The crystal perfection of epitaxial layer can never exceed that of the substrate, and frequently can be measured. So this diagram states that we can have 5 types of defects. So first, suppose one line dislocation is present in the substrate, that will be extended to the epitaxial layer. Second is the stacking fault. If some stacking fault is there at the boundary, it will lead to some epitaxial defect. Then impurity precipitation will be there, some disalignment will be there, and some bulk stacking fault will be there. This is the bulk stacking fault. So this is all about the epitaxial process, that what are the process parameters which are used to control the epitaxial process, that how much is the temperature, how much is the pressure, and how we can choose the compound, how we can select the starting compound, what should be the starting compound of the to start the epitaxial process, and how and what are the defects which can be present in the final result. Thank you.